Okay. So, just in that previous equation, right, previous equation we just saw, no, that is your T m minus T e divided by V a base divided by omega 0 m, and this is basically nothing but the torque base. This is nothing but the torque base. That means this equation will become T m by torque base minus your T by torque base, right. So, this T by T base is equal to T bar, T m bar we are writing here, and T by T base also T bar, right. So, in per unit, this is per unit, and this one omega r upon dt we are writing from previous equation we have written, no, omega r upon that omega 0 m, this is actually nothing but omega r bar. So, this is 2h d omega r bar dt is equal to T m bar minus T bar. That means, all these quantities are in per unit, right. So, and this is no need to read, this is equation 178. So, we have seen omega r bar is equal to omega m upon omega 0 m. So, this we can write that omega r upon P f divided by omega 0 upon P f, right. This is basically your field poles, P f is field poles, is equal to, we can write omega r upon omega r bar is equal to omega r by omega 0, right. So, actually things are simple, just we are transforming it to per unit values. So, where omega is the angular velocity of the rotor in electrical radian per second, and omega 0 it is rated value, and P f is the number of field poles, right. So, if delta is the angular position of the rotor in electrical radians with respect to a synchronously rotating reference, and delta 0 is initial value say at t is equal to 0, then we can write delta is equal to omega r minus omega 0 into t plus delta 0. This is equation 179, right. So, this is no need, this is no need, only this is equation 179 and this is equation 180. That means, if you take the derivative of it, so d delta by dt will be omega r minus omega 0, and this is nothing but is equal to delta omega r, right. If you take the double derivative of it, then d square delta is equal to dt square is equal to d omega r by dt is equal to d dt of delta omega r, right. Therefore, this d square delta dt square is equal to omega 0, right, into your d dt of omega, I mean you numerator and denominator you multiply by omega 0. So, this equation you are writing omega 0 d dt and omega r by omega 0, you are dividing it by omega 0, and here it is omega 0 is equal to, you can write omega 0, then d omega d dt of omega r bar, because this is now per unit values, right, is equal to, we can write that omega 0 d dt of delta omega r, right, because earlier we have seen that your here that omega r bar is equal to omega r upon omega 0, right. So, and here it is your delta omega r minus omega 0 is your delta omega r, right. Therefore, this one if you take that your omega 0 into d omega r by dt, this is omega r bar, right. So, is equal to, we can write omega 0 d of dt delta omega r. I mean this one also you can call, I mean this is delta omega r. So, if you take the derivative of this one, it is d omega r by dt, that is d dt of delta omega r. So, that means we can make it that d omega r by dt omega r by dt is equal to d dt delta omega r bar. I mean it is something like this, it is something like this. Suppose you take this equation, you take this equation, right. Say both side you divided by your what you call that 0, right, omega 0 is equal to d dt delta omega r by omega 0, right. So, this will become your d omega r bar dt, because omega r bar this one, and d dt of delta omega r upon omega 0, this is your base value. So, this will be per unit values. So, it will be delta omega r, that is delta omega r bar d dt of delta omega r bar, right. So, from this only we are writing it that this is very interesting. from this we are writing omega 0 d dt of omega r bar is nothing but omega 0 d dt of delta omega bar r bar, right. So, this is equation your what you call, this is equation 181, and this one, this is nothing, this is for my own reference because this is my class note. So, this is actually equation 181, right. So, that means from equation 178 and 181 you will get 2h upon omega 0 d square delta upon dt square is equal to T m bar minus T bar, all are in power unit. This is equation 182, right. This is actually nothing, only this one, right. So, next is it is often desirable to include a component of damping torque, right, and not accounted for in the calculation of T separately. This is accomplished by adding a term proportional to speed deviation in equation 182 as follows. Therefore, we can add one damping term, that is 2h upon omega 0 d square delta upon dt square is equal to T m bar minus T bar minus k d into delta omega bar. This is equation 183. This one you should not see. This is my, again and again I am telling, this is my class note. So, this is for my own reference, right. So, T m bar minus T bar minus k d into delta omega bar, that is equation, this damping term is added, right, where delta omega bar I told you earlier is equal to delta omega bar upon omega 0, right, is equal to, we can write 1 upon omega 0, and this is actually d delta by dt, right, delta omega r. Therefore, that 2h by omega 0 d square delta upon dt square is equal to T m bar minus T bar, then this term minus k d term is there, right, and what actually has been done, that is delta omega r bar is equal to 1 upon omega 0 into d delta by dt. This thing that your this omega bar is equal to this one has been your substituted here. If you substitute here, you will get minus k d upon omega 0 into d delta by dt, right. Therefore, this equation is coming, it is here, right. Therefore, 2h, now both side you multiply by omega 0. So, it will be 2h d square delta upon dt square is equal to omega 0 in bracket T m bar minus T bar minus k d into d delta by dt. If you multiplying both sides by omega 0, this omega 0 will be cancelled. So, minus k d upon a k d into d delta by dt. This is equation 183a, right. So, equation 183 represents the equation of motion of a synchronous machine, right. I mean this equation 183, right. It is commonly referred to as the swing equation because it represents swing in rotor angle delta during disturbances, right. So, it is commonly referred to as a swing equation because it represents swings in rotor angle delta during any disturbances, right. So, next is per unit moment of inertia. So, from equation 183a, that means this equation, from this equation, right, 2h upon omega 0 d square delta dt square T m bar minus T bar minus k d upon omega 0 into d delta upon dt. This is equation 184. This one you should not see. This one you should not see, right. This is equation 184, right. So, therefore, you multiply this equation numerator and denominator by 2h omega 0. So, by omega 0. So, numerator will be 2h omega 0 and denominator will be omega 0 square into d square delta upon dt square is equal to T m bar minus T bar minus k d upon omega 0 into d delta by dt, right. Now, we know that earlier we have seen T base is nothing but 1 upon omega. So, it is 1 upon omega 0 is a time base, right. Therefore, T by T base is equal to T bar. Actually, this is actually time, it is actually T. T by T base is equal to T bar, right. Time, if you take time in per unit, and T base is equal to 1 upon omega 0. If we do so, that means my T base is 1, that means my 1 upon omega 0 square will be my t base square. It is coming from here, it is coming from here, right. That means 1 upon omega 0 square, you can write 2h omega 0 is okay, this is 2h omega 0, and 1 upon omega 0 square, it is t base square into d square delta dt square equal to t m bar minus t or t bar, and 1 upon omega 0 is equal to t base, because 1 upon omega 0 is equal to your t base. So, we are multiplying minus k d into t base, because it is 1 upon omega 0 into d delta by dt. This way we write, right. Next is, and if we want to represent time in per unit, generally we represent in our all the quantities in per unit except time, but if we want to represent time in per unit, so what should be the technique? Then this 2h omega 0 is okay, then this is d square delta dt square. So, we can write d square delta d of t upon t base square, right, because this t base square has been has been written here t by t, your what you call that one t is missing, that is your, it is t base, right, it is t base, right, t base square. So, d square delta upon d of t by t base square, because this one has been taken here, that is by this thing, or what you call that t by t base, right. And similarly, here also it is your minus k d d delta d upon t base, this has been written like this. Therefore, t by t base is nothing but t bar, the time in per unit. Therefore, we can write 2h omega 0, then d square delta, then d t bar square, right, is equal to t m bar minus t b bar minus k d d delta upon d t bar. That means, all these quantities for this equation 185 is in per unit, including time, if you want to represent time in per unit. Generally, in stability studies, only time we generally represent in second, but other quantities we see your what we call represent in per unit values, right. So, now some authors have written, I mean many researchers or authors, they refer to 2h omega 0 as the per unit moment of inertia, that is j bar is equal to 2h omega 0, because h, you have seen from your stability studies that unit or dimension of h is in second, inertia is in second, and omega 0 is radian per second. So, finally, 2h omega 0 will be a dimensionless quantity. That is why some authors they refer this one as the 2h omega 0 as the per unit moment of inertia. That is why you are putting j bar. That means, everything, if you see that everything will be per unit, that this equation if I write like this, that j bar, then d square delta dt square is equal to t m bar minus your t bar minus k d, then your d delta by dt, right. So, everything is in per unit, right, all these quantities are in per unit. So, now next is that a mechanical starting time. Now, from equation 178 rather, from equation 178 we can write that d dt of omega r bar is equal to t m bar minus t bar upon 2h, right, is equal to, we can write 1 upon 2h t a bar, that is the accelerating power, t a is equal to t m minus t, we know. So, t a bar will be t m bar minus t bar. So, 1 upon 2h t a bar, right. Now, if you integrate with respect to time, then omega r will give 1 upon 2h 0 to t t a bar dt. This is equation 186, right. Now, this is some approx rough calculations that your mechanical starting time. Therefore, now let T m be the time required for rated torque to accelerate the rotor from standstills to rotor speed, right. I mean, if you assume that T m be the time required for rated torque to accelerate the rotor from standstill to rated speed. Now, from equation 186, this one, with omega r bar is equal to say 1 per unit and T a bar is equal to say 1.0 per unit, and with the starting value of omega r bar is equal to 0, say initial value, the starting value is 0, right. Then you can see that your what you call 1 is equal to, because omega r we have taken 1 upon 2h 0 to 2m, here also T a bar we have taken 1, right, into dt. So, it is T m upon 2h, right. That means, we can write T m is equal to 2h second. So, T m is called the mechanical starting time. It is some rough calculation, it is some approximate calculation. So, Tm is called the mechanical starting time. So, it is 2h second because dimension of h is in second. Now, calculation of inertia constant. So, now we know from our power system studies, power system analysis, transient stability studies or in machine that H is equal to stored energy at rated speed in megawatt second divided by MVA rating, right. So, it is a unit is second, right. Therefore, stored energy is nothing but is equal to kinetic energy. So, we can write kinetic energy is equal to stored energy half j omega 0 m square, that is watt second, because energy is joule and we know joule per second is equal to watt. So, joule is equal to watt second. So, we write in watt second rather than joule, right. So, we can write now if you convert watt into megawatt, then it will be half j omega 0 m square into 10 to the power minus 6 megawatt second, right, because 10 to the power 6 watt is equal to 1 megawatt, right. So, that is why your half j omega 0 m square into 10 to the power minus 6 megawatt second. Now, j is equal to your moment of inertia in kg meter square, this we know. Omega 0 m is rated speed in mechanical radian per second, right, is equal to 2 pi into revolution per minute rpm by 60, that is omega 0 m, right, in because we are giving in radian per second. Now, therefore, this h will be equal to half j omega 0 m square into 10 to the power minus 6 divided by MVA rating, right, because this is that equation, this is the equation and divided by MVA rating. Now, this is equal to h is equal to half j omega 0 m is equal to 2 pi the revolution per minute, I write rpm divided by 60 square into 10 to the power minus 6 divided by MVA rating. If you simplify this one, it comes actually 5.48 into 10 to the power minus 9 j rpm square divided by MVA rating, that is equation 187, right. Now, this is actually value of h. This is from for the point of view of solving numericals, this you have to keep it in your mind, I mean keep it in your memory, right. So, typical value of h. So, generally for a machine that 3600 rpm or 3000 rpm, right, basically 2 pole machine for thermal power plant thermal unit, h generally lies in between 2.5 and 6.0 second, right. And if it is 1800 rpm or 1500 rpm, that is 4 pole machines, so h generally lies in between 4 and 10 second, right. And similarly for hydro unit, hydraulic unit, h generally but typical values lies in between 2 and 4 second, right. So, this is actually your what you call different values of h, range of values of h for thermal or hydro power plant. Now, representation in system studies, right. Now the state space form requires the your what you call the component models to be expressed as a set of first order differential equation, because slowly and slowly we have to go for the your what you call development of your first order block, your what you call block diagram representation of the synchronous machine, right. So, the state space form requires the your component models to be expressed as a set of first order differential equations. The swing equation, that is 183, expressed as two first order differential equations, it becomes actually d dt of delta omega bar is equal to 1 upon 2 h T m bar minus T e bar minus k d delta omega r bar. This is equation your 188, right. So, this is 100, this is nothing, this is also nothing, and d delta upon dt is equal to omega 0 delta omega r bar. This we have seen this, right. Now, in the above equation, time t is in second, because here we are not using bar t bar, it is time in second, and rotor angle delta is in electrical radian and omega 0 is equal to 2 pi f, right. So, now the block diagram representation of equation 188, that means these two equation, and 189 is shown in figure 18, right. Now, question is that assuming all initial conditions are 0, if you take the Laplace transform of this one, right, so it will become s into delta your delta omega bar s, s will not put again and again, right, understandable. So, it will be s into delta omega r is equal to 1 upon 2h, it will be Tm bar minus T bar minus Kd delta omega r bar, right. I mean, if you look into this, that if you take the Laplace transform on both sides, so again and again I am not making this quantities function of s, understandable, only s I will put. So, it is s, right, then delta omega bar is equal to 1 upon 2h, right, then Tm bar minus T bar minus Kd, then your delta omega r bar, right. This way you can write. Now, if you go for cross multiplication and simplify, then what to write? I am writing here, just see that, then 2hs you go for cross multiplication, and after cross multiplication bring Kd omega r term to left hand side. So, it will be Kd, right, into your delta omega r bar, because here delta omega bar, here also delta omega bar is equal to your Tm bar minus T bar, right. So, 2hs plus Kd term will be there. Therefore, delta omega bar will be your Tm minus T divided by 2hs plus Kd, right. So, that is why this block diagram, if you look into that, Tm bar is given input here and T bar. So, this one, this output is Tm bar minus T bar into, and delta omega r will be your what you call your Tm bar minus T bar divided by 2hs plus Kd, that we have seen, and this output is delta omega r bar. Now, again if you see this equation, that your this equation, if you take your what you call that your Laplace transform, again and again not putting the function of this thing, just hold on, just this thing, then this one, if you take s delta is equal to omega 0 delta omega r bar, right. This is there, therefore, delta will be is equal to omega 0 by s into delta omega r bar, right. So, that is why here we are writing that delta is equal to omega 0 by s into delta omega. This is the first step, slowly and slowly it will grow, right. I mean, just step by step it will grow, later you will see it will be a very big model, just hold on, slowly and slowly we are it will be growing that step by step, right. So, this is actually, then we can write Tm bar, then this is Tm bar and this is a minus 1 T bar, and this block diagram you put 1 upon 2hs plus Kd, this output is delta omega bar and omega 0 by s into and this output is delta, right. So, up to this is no problem at all, it is very simple thing, right. This is my figure 18, that is block diagram representation. Now, synchronous machine representation in stability studies, we have to make few assumptions. Now, for stability analysis of large system, it is necessary to neglect the following terms from equation 118 and 119 for stator voltage. So, whenever you will listen to this course, right, this as all these notes will be provided to you. So, keep everything ready in front of you, because if I do not want to go back again 118 and 119, for example, many such things will come. So, you will keep those things in front of you and just see this, right. So, that from equation 118 and 19 for stator voltage rise, it is necessary to neglect the following terms. The first is that transformer voltage terms P psi d, that is psi d dot, and P psi q, that is psi q dot, this will be dropped, right, because we are, and similarly the effect of speed variation, this also will be dropped, right. If it is so, the P psi d and P psi q terms represent the stator transients, right. With these terms neglected, the stator quantities contain only fundamental frequency components and the stator voltage equations appear as algebraic equation, right. That means, with the stator transients neglected, the per unit stator voltage equation 118 and 119 appear as algebraic equation. So, P psi d and P psi q terms will be dropped in equation 118 and 119. Actually, what I have done is this, I did not break this thing, this equation number will increase, right. So, such to maintain the continuity. So, I perhaps I feel that it will be very helpful for you people, because when I have taught this course here, their students also find these things are quite useful, right. So, that is why that equation number will continue, and it will cross it will have so many equations such that there will be a continuity or link, right. That is why this equation number, so there are nothing to be surprised looking at equation 190, 191 or 200 or more, right, but it will help you a lot, but because continuity will be there and you can link one after another when you will have these nodes, right. So, that is why that means this equation, your what you call this equation, that your 118 and 119, right. So, this is no need to see, this is no need to see. So, it is equation 190 and 191, right. Therefore, E d will be minus psi q omega r and minus R a I d, and E q will be psi d omega r minus R a I q after dropping p psi d and p psi q terms, right. So, another simplifying assumption is, we have to make many assumptions. Another simplifying assumption is that the per unit value of omega r is taken 1.0 per unit in the stator voltage equation. This is not same as saying that the speed is constant. It assumes that speed changes are small and do not have a significant effect on the voltage, right. So, this sentence is very important, that in the stator voltage equation, this is not same as saying that speed is constant, rather it assumes that speed changes are small and do not have a significant effect on the voltage, right. So, the assumptions per unit omega r is equal to your 1, that is omega r is equal to omega 0 is equal to this thing omega 0 radian per second in the stator voltage equation does not contribute to computational simplicity in itself. The primary reason for making its assumption is that it counterbalances the effect of neglecting p psi d and p psi q terms so far as the low frequency rotor oscillations are concerned. We will see those things in later, right, much later, right. With omega r is equal to 1.0 per unit, the stator voltage equations reduce to that E d will now here in this equation, if omega r is equal to 1 per unit, then this your what you call, then E d will be equal to this is not required, right. So, this is for my own reference. So, E d is equal to minus psi q minus R a I d, this is equation 192, and E q will be psi d minus R a I q, this is equation 193, right. So, that means we are simplifying one after another, right. So, now okay. So, we will thank you very much, we will be back again.